So first of all, thanks Barbara and Claude for inviting me. I'm going to be talking about a very different type of extensional systems. These are magma-poor systems. Here we see very little evidence of magmatic activity during crustal stretching, and even when crust is completely broken up, we don't see an abrupt transition to oceanic spreading, but often we see wide transitions of exhumed and serpentinized mantle. So this is a presentation of some work that I have been doing for some years now in collaboration with colleagues. I'm going to first talk about the observations. I'm going to describe the kinematics of faulting and crustal thinning and how we think asymmetry of conjugate margins forms. Then I'm going to use some numerical models to explain the dynamics of asymmetry formation. And finally, I will be talking about the relationship between a strain localization and the onset of melting and oceanization at this type of margins. So if we want to understand magma-poor margins, there are three key questions that we need to address. The first one is, how do we create asymmetric conjugate margins? At the start of extension, we have systems which do not show any preferred orientation of faulting, and at the end of extension, we often find conjugate margins where one of the margins presents abundant faulting in the upper crust and a smooth crustal thinning, and the other margin presents much abrupter crustal thinning and much less faulting. We would like also to understand how this asymmetry formation is related to the pattern of faulting and to the changing geometry of these faults as extension increase. So normally we see planar faults, planar normal faults at the continental platform, going to listric geometries at the necking area, and detachment-like faults at the breakup, at the very thin breakup margins. And finally, we would like to understand the relationship between the pattern of crustal thinning and margin architecture and the type of continent-ocean transition. As I mentioned, some of these margins present a broad zone of exhumed and serpentinized mantle between the thin continental crust and the oceanic crust, but the others do not show clear evidence for that. So I will first start with the observations, and I will mainly focus on the West Iberia Newfoundland margins. These are one of the best studied magma-poor margins, because there have been many 4 IODPs here and many seismic surveys. This is a typical cross-section at the margin. This is Iberia, Newfoundland, this is continental crust, and here we have the transitional zone. Velocities of extension derived from IODP drillings and modeling of magnetic anomalies suggest that the velocities of extension are very slow here. They are well within the ultra-slow end member for oceanic crust, typically 4 millimeters per year half spreading. In Iberia and in some other margins, PTT data indicate a cool mojo at the start, 450 to 600 degrees. Both slow extension and very and rather cold initial temperatures at the mojo indicate a lower crust that is rather strong during rifting, so that it couples the formation in the upper crust with the formation in the mantle. So this is a PTT path for a rock that was sitting close to the mojo at the start of the Jurassic rifting in one of the ancient Tethys margins that is now exposed in the Alps, and it shows evidence for conductive cooling due probably to very slow extension during rifting. If we do very simple numerical models of this temperature evolution, and we look at the consequence for crustal rheology, what we see is the following. We have at the beginning of extension a lower crust that is rather ductile. As extension increases, this lower crust cools and it becomes increasingly brittle, and so it's exhumed by deep penetrating folds. At some point during extension, the extension factor will depend on exactly the lower crustal rheology that you use and the extension velocity. You get whole brittle crust, so you get deep penetrating folds reaching into the moho. So in summary, we have an initial upper crust which is brittle, lower crust which is ductile. With increasing extension and cooling, deep penetrating folds exhume lower crust. At some point, these folds reach into the mantle. They bring enough seawater to serpentinize it, and because serpentinites are very weak, this area of serpentinite's mantle forms a weak area that further attracts the formation, and through which crustal breakup and mantle exhumation occurs. So, how do we go from this basin stage where there is no preferred orientation of faulting to a margin stage? To understand the basin stage, we have looked at studies at very little extended basins, because in Iberia and Newfoundland, we only see the last phases of breakup. And in particular, we have looked at the East Shetland Basin. This is a study of Cowie et al., which shows the topography of, or the bathymetry of the basin at the end of the late Jurassic rifting. We see a series of folds that increase in throw towards the rift axis. These authors had access to very good stratigraphy data from which they reconstructed the tectonic history of the basin, and they showed that extension started with many small folds dipping outward and inward, and were active at the same time. As extension increased, these folds linked laterally, some of them died out, and acquired a dominant sense of dip towards the basin center. And as extension further increased, the folds farther away from the basin center died out, while those closer to the basin center continued to extend. This type of fold evolution is observed at many rift basins, like the Gulf of Corinth and the Gulf of Suez, and it seems to be a general pattern of evolution of fold systems. So to understand the margin stage, we have looked at the West Iberia Newfoundland systems. So this is West Iberia and Newfoundland reconstructed at the time of the breakup. The red dots are IODP drillings. The white triangles is a peridotite ridge exhumed at the surface. And I'm going to show you a pre-stack depth migrated line shown in white, which shows how the continental crust thins from about 18 kilometers to the exhumation of the mantle. And this is here. So we see a series of rotated blocks bounded by folds. Here they are overlaying a detachment-like fold, and just oceanward of it, we have the mantle exhumed at the peridotite ridge. So from IODP, we can constrain, at least partly, the syn rift of these blocks, at least block B3 and B5, and we see that this syn rift yawns towards the ocean basin in a similar way that it was described for the East Shetland Basin. So we can measure the angles of these folds, and they are all within normal Andersonian angles from 60 to 30 degrees. The dimensions of these fold blocks decrease basinward because the dimensions of the fold block is related to the dimension of the brittle layer, this implies that each of these faults cut through a brittle layer that was thinner, because the brittle layer in this case comprises the upper crust and the lower crust. It means that each of these faults cut through a crust that was progressively thinner. So our interpretation is that these faults were sequential in time, and they were active one after the other, cutting a crust that was progressively thinner. So to conceptualize this model, we have built a kinematic model that summarizes this. And this is basically shown here. This is the evolution for the basin stage, mimicking what we learned about the East Shetland Basin. So we have distributed faulting active at the same time at the beginning of extension, and concentrating and localizing towards fewer and fewer faults, which die out and continue to be active towards the rift basin. The new component that we added here is that we assumed that crustal thinning occurs by the same amount as extension unfolding, and that it occurs directly underneath where faulting is occurring. So first, crustal thinning is distributed, and as a strain is localized in less faults, a crustal thinning also becomes localized. At this point, this fault has rotated as much as it could to 30 degrees, and a new fault starts at the hanging wall of this fault where the crust is thinnest. And this is the beginning of sequential faulting. So in building this model, we have taken into account some rules, and these are area conservation. And the important thing here is that when we go to the sequential faulting stage, because most of the crust is brittle, when we cut a new fault, if this rotates, the area underneath these fault blocks needs to conserve, and so this fault that was planar becomes progressively listric once it is not more active. And in this way, as you will see, we form these detachment-like structures. So now this is fault F1. This is the fault that we see in the pre-stack seismic section I showed you earlier. And I'm going to rotate this fault by the degrees I measured on the profile, and then I'm going to do the same with F2, F3, etc. So this is F1, F2, F3, and you see how faults that were planar, like F2, become listric, and the progressive action of this sequential fault array creates these detachment-like structures and two asymmetric conjugate margins. So these detachment faults can be explained without having structures being active at low angle, and they result from the action of an array of faults that are sequential in time and are active at normal angles, and form a result in this conjugate margin asymmetry. So we can reproduce the geometry of faulting from normal to listric to detachment-like just by having an array of sequential faults dipping towards the oceans. Another implication of this is that the early pre-rift and syn-rift that is deposited at the early stages of rifting will be found on top of very thin crust at the deep margin without the need of invoking anomalous subsidence. And finally, if this period of sequential faulting is long enough, sediments that are deposited here after these faults stop to be active may have post-rift geometry, but may actually predate the age of breakup here. And this is actually an observation that is common in the South Atlantic margins. Okay, so what are the reasons, the dynamic reasons for these kinematics? This is numerical experiments, finite element experiments performed by Sascha Brune from Potsdam that address this question. So that's the initial configuration of the experiment. He has a 130 thermal lab, compositional lab at 90 kilometers. And for his standard model, he used mafic crust because wide-angle profiles appear to have 6.7 to 6.9 velocities in the lower crust, which indicate perhaps a more mafic rheology. But as you will see, we have also done experiments with more felsic rheologies and have the same result. So that's a numerical experiment for full extension velocity of 8 millimeters per year. So that's very slow extension velocity. On top, we have a strain rate. Here we have upper crust, lower crust, and lithospheric mantle. And we see at the beginning we have a strain localized in an array of distributed faults. Because of, I have failed to mention something, and that there is a strain softening all in upper brittle layers as well as in the viscous part of the lithosphere. And because this strain softening, a strain tends to finally localize on a single fault that couples the formation from the upper crust to the mantle. So forming a huge fault that leads to upwelling of the hot asthenosphere at the downward tip of this fault. This asymmetric upwelling keeps always weakening the hanging wall of the main fault, so that the hanging wall of each of these new faults is always weaker than its foot wall. And this leads to the generation of an asymmetric array of sequential faults that result into asymmetric margin structures. In red, you see the contours of melt. For this very slow extension velocity, the underplate of melt, if it all could go up into the crust, could be 1 kilometer only. At some point, crust finally breaks up, and we have final crustal breakup and lithospheric breakup. Okay, so this is the process in more detail. This is a strain rate, viscosity. You see, because of this strain localization, isotherms are going up at the hanging wall part of the fault, creating a low viscosity pocket in the lower crust, which promotes fault migration towards the ocean. Okay, another important point here is that if we look at the extension velocity, this is horizontal extension, because when we go to fault localization and sequential faulting, only one fault is active at a time for around 1 million years. These faults accumulate a very high extension velocity because they are accumulating the whole extensional velocity in one single fault. So we have actually a very slow extending system with a fault that presents a very high slip rate. So the fault pattern evolution looks like this. Red faults are active, so we have distributed faulting going into sequential faulting. As sequential faulting starts, this becomes abandoned and forms sac basins, as those observed in the South Atlantic, and finally we go to break up. Now, the distribution of sequential faulting towards distributed faulting depends on the ability of the lower crust to flow. This is the same than saying that the width of the white margin depends on how much the lower crust can flow into the tip of the active fault. If the lower crust is very weak, the lower crust can flow a lot, and it replenishes the thinning crust, and then crustal faulting is not very effective at at thinning the crust. If the lower crust is much stronger, crustal faulting is much more effective at crustal thinning. So lower crust can be weak either because it is initially weak or because the velocity of extension is very high and it maintains the isotherms at a higher level during extension. So we can look at the influence of extensional velocity. We see here full extensional velocities going from 4 to 10 million years, and the phase of sequential faulting increasing from 60 kilometers to 230 kilometers. And this is because conductive cooling here is much less effective, and thus it creates a much longer and wide margin. These geometries reproduce very well what we see in the Brazil-Angolan margin, and in general, it can also reproduce the width of the margins at the South American, African margins. So this is the stage just at the onset of seafloor spreading of the two margins. The stage pole is something somewhere around here. Because of these, linear velocities increase oceanward. So if we use these linear velocities deduced from kinematics and model them, we find these widths of the margins represented here by yellow blocks is the African margin, the green block is the South American one, and they reproduce quite well the width of these two margins deduced from the data, which are here shown in green and yellow lines as well. So the lower crustal rheology, the initial lower crustal rheology has, of course, also an effect on the width of these margins. If the lower crust is stronger, then the phase of distributed faulting is shorter and of sequential faulting as well, because crustal thinning is being more effective. If the lower crust is weaker, the phase of distributed as well as the phase of sequential faulting is much longer, leading to a much longer wide margin. And if the lower crust is very weak, then because the lower crust is flowing always towards the tip of the active faults, there is actually no sequential faulting phase, and all we have is distributed crustal faulting with lower crustal flow underneath and two symmetric margins. The importance of this is that here we will see sac basins which have an age which predate breakup, and here we shouldn't see them. So this gives us a way to understand how the margins have worked. Okay, so finally, I will go to the last part of my talk. This is what I actually wanted when Barbara approached me. This is what I actually wanted to present. This is how strain localization relates to the way melting and oceanization starts. And this is, you will see, is work in progress. I actually haven't had the time of doing this because my 3 months daughter has taken much more time of me than I expected. So, okay, so in a nutshell, the key point that I want to address here is that if there is no effect from a strain localization during continental extension, the type of melting curves that we get during continental rifting are very similar to those for oceanic spreading. So for a certain velocity, we generate a certain melt thickness, and that's it. This pattern Okay, so and this is one of these experiments, numerical experiments with no strain localization. So this is progressive extension. Here you see the mojo, the brittle ductile transition, and at this point faults get into the mantle, they bring sweet water, they serpentinize, the green is serpentinite. This is the base of the continental lithosphere. So because this is very slow, melting only starts once the mantle has been exhumed at the surface. So you have this layer of serpentinized mantle at the surface and melting occurring at the bottom, because this layer may be anisotropic in the direction of extension. It may prevent the melts to go up, and so we apparently have a wide continent-ocean transition with serpentinites on top and the melt ponding below. If localization is taken into account, the amount of melting, the amount of melting is not only a function of velocity, but also it's a function of the way that strain is localized during rifting. So, for example, here we have two numerical experiments. This, I'm showing here to a depth of 40 kilometers. This has a strong lower crust rheology. This has a weak lower crust rheology. The strong lower crust is very effective at crustal thinning, so leads to a very short phase of distributed faulting and a very short phase of sequential faulting and very slight asymmetric margins. The weak rheology is not effective at crustal thinning, so lower crustal flow always flows into the tip of the active fault and creates two asymmetric margins with sequential faults on top. Okay, so what are the implications of this for melting and serpentinization? So here we have the results for the strong lower crustal rheology. Here it's the weak one. This is a strain rate. This is going to be accumulated serpentinization, so that's 30 kilometers. 30 kilometers depth. That's area of melt production for both models up to 80 kilometers depth. And this is magmatic crustal thickness if all the melt would rise up and would be accumulated at the center of the rift. So for the mafic granulite, crustal thinning is very effective, and serpentinization starts early in the rift history because crustal breakup also occurs early. For the weak rheology, the mojo is here, and we have a very ductile lower crust, and here we have not started serpentinization at all. Instead, we have started a little bit of melting, which we have also at this point. But you see that the amount of melting produced here is much less than there, because here the strain coupling between upper crust, lower crust, and mantle is much less than in the case where the lower crustal rheology is strong. So for the same extensional velocities, we have two very different scenarios for the onset of melting. As extension on goes, oceanization may start before in this scenario with a strong lower crust than in the scenario with weak lower crust, where we keep extending and thinning the crust for hundreds and hundreds of kilometers before final breakup occurs. So in summary, we have seen that the asymmetry of these margins is the result of the emergence of an array of sequential faults that dip consistently towards the ocean, that this sequential fault pattern arises due to progressive strain localization between upper crust, lower crust, and mantle, that the width of the white margins depends on lower crustal rheologies, and that the weak lower crust rheologies tend to promote white margins with very thin crust, less than 10 kilometers over very wide widths. And finally, the onset of melting and serpentinization is also related to lower crustal rheology and its ability to couple the deformation from upper crust to mantle lithosphere and asthenosphere. Thank you very much.